All right. Yeah. So on January 7th, 2015, I appeared via Skype on this event from my kitchen in pyjama. So yeah. Now I'm going to give a talk in person, and the talk is titled "Smart Money Between Digital Money and Smart Contracts," and I'm inviting you to dig deeper today into the nature of money, nature of contracts, and what can we have in between. All right. So let's start with Bitcoin. Right. So what's new in Bitcoin? There are three things, in my opinion. So the first thing is the blockchain itself. So a permanent transaction lock that is maintained via consensus in permissionless decentralized network. So yeah, the very first solution for such setting for the consensus problem. And many applications could be built on top of that, but to the moment, it seems only financial applications do have success, maybe for a good reason. But that's a topic for a dedicated talk, probably. The second thing is that the Bitcoin is a first digital scarce resource, right? So kind of digital gold. And under certain cryptographic assumptions and also honest mining majority assumption, Bitcoin is even better than gold, right? But even this statement is mind-blowing, right? Because when we are talking about financial instruments and gold, so they don't rely on cryptographic assumptions or honest majority assumption or whatever. So we have a new kind of financial instrument, and this is a topic for another dedicated talk, probably. Third new thing about Bitcoin I'm going to dig into during this talk is that Bitcoin is kind of smart, or I'm calling this also contractual money, right? What does it mean? So what was before the Bitcoin? Very simple. So we have money, right? Like this paper note. You know, there is some contract behind this note, certain national and in case of Eurozone also pan-European laws, but 99% of note users do not know about these contracts and don't have any control, right, basically on individual level. The contractual possibilities, right, of this note are very limited. For example, if I put this note on the table, right, then whoever comes first can possess it easily, right? With Bitcoin, we are getting a new kind of digital money. So before the Bitcoin, digital money were just a substitute for this paper note, right? So you have some digits on a screen, right? Then supposedly these digits are backed by something. Maybe not really, I mean, but still this is about a very passive entity, right? What you are seeing on screen. Now with Bitcoin, you have a digital note, right? In the digital world, there is no need to have for a fixed nominal, so we have arbitrary nominal, right? 0.2517 Bitcoins. And also we have individual contract for each node, right? Usually a contract in Bitcoin is about something like this statement. So this node could be spent by providing a signature which is corresponding to public key of Alice on a spending transaction bytes, right? But this contract is stated not in the text, definitely, right?
1 second, I'm just going to back your mic up. So you back up a bit because our shot.
All right, all right.
Thank you.
All right, so these digital nodes have contracts set in form of executable code, right? So this is the same contract, but in the Bitcoin script programming language, right? So things are getting complicated, right? Now each node is coming with an individual contract, right? And what is a money transfer in Bitcoin? So to transfer money in Bitcoin, first you need to provide arguments to the contract, to the program, right, of a digital node. And with proper arguments, this program is being evaluated to true value, right? So there are two possible outcomes of execution, so true or false. If outcome is true, then this node is spendable, right? And then your digital node is getting destroyed, right? So it's been removed from the current state. And instead, new digital nodes are being created, right, with some new programs. So that's how Bitcoin works. However, when you are sending money by using your wallet, right, it is usually hiding all the complexities. So you are just thinking you are sending 0.1 Bitcoin to another public key, but actually under the hood things are more complicated. All right, and even more complicated nature of Bitcoin transactions we have. That is, a transaction can have multiple inputs, right? So consume many digital nodes and also can create many digital nodes, right? So input nodes are called inputs in Bitcoin, output nodes outputs, and in order to check arbitrary transaction, you need to know current unspent transaction output set, right? So which nodes are active at the moment, which nodes are spendable, which nodes could be destroyed by providing proper arguments. All right, so what kind of programs can you do with Bitcoin? Actually, Bitcoin scripting capabilities are very limited, so we have a few cryptographic instructions. So check sig, check signature, check multisig. Multi-signature, you can do hashing, some arithmetic, logic, bitwise operations, no cycles, right? To avoid situation when your money can get stuck in a cycle, which is pretty absurd in the real world, but could happen in the digital world. And starting from Bitcoin 0.12 or 0.13 maybe, it is also possible to check current time and block height in a script. Right, that's it. And actually, many operations were switched off during denial of service attacks Bitcoin had from 2010 to 2012. Some were pretty painful to the network. And in the worst case, which did not happen in the mainnet, but was discovered and shown in the testing network. So it was about 6 hours on average computer to validate a transaction, right? So you have 10 minutes between blocks, but 6 hours to validate a block, which is about very unclear security consequences, right? All right. And program size is also limited in Bitcoin. So you can have no more than 10 kilobytes of programming code within a digital node. All right. People try to do complicated contracts on top of Bitcoin. It was a startup called Lighthouse, which tried to do crowdfunding campaigns. And I believe it failed, so I didn't hear about them for years. It also was a startup called Colu, which was about issuing your own local community currencies. And now, as far as I know, they are doing something on top of Ethereum. Right, so people try to do something on top of Bitcoin. Some contracts are possible, like Lightning Network contracts, atomic swaps, etc. But people did want to do something more powerful. So started from 2012, many new altcoins appeared, starting with Namecoin, then Beaches, NXT, then Ethereum. And in Ethereum, we don't have this digital nodes notion anymore. We have just a smart contract as a dedicated entity, which is getting some transactions as inputs and producing some transactions. So it's more complicated, probably, model. And even more, one contract during execution can call another contract, so you can have a chain of calls, right? So what's good about Ethereum? So it has so-called Turing completeness. In principle, you can do anything on top of the Ethereum platform, in principle, right? And also, it is easy to develop contracts by using some high-level language, for example, JavaScript like Solidity, right? Well, good things are over. Now about some disadvantages of the Ethereum. So still you can do very limited applications, right? Because many things are simply way too expensive. So as you probably know, you need to pay for execution in Ethereum. There is notion of gas, right? And there is some block limit for gas. For many non-trivial applications, you cannot do anything within a block, right? So you need to forget about your application to be built on top of public Ethereum blockchain then. All right, and also Ethereum is a security nightmare, right? Because things are pretty complicated. You probably know about the DAO hack, right? Which was about these calls, about a call semantics not properly understood by a developer, and also, in fact, Solidity language did hide complexity behind these semantics. Also, you probably know about this parity multisig library bug, which was about $35 million lost because some schoolboy, according to a legend, destroyed library contracts with kill signal sent to the contract, to the library contract. And so on and so on. And also, Ethereum now has scalability problems with its bold state. State is all the active contracts at the moment, right? And its design is not friendly to stateless clients. There is a paper of my co-authorship on that, Hydra, a cryptocurrency with stateless transaction validation, so it provides some details I'm going to skip right now. And now I'm proposing to do one step back and then one step right, or maybe one step in a right direction. So let's go back. from Ethereum smart contracts to Bitcoin's smart digital nodes, right? Digital coins. And let's try to do most of Ethereum use cases on top of modifying Bitcoin approach, right? So I'm going to talk about languages which are implemented on top of Ergo blockchain. So there is some internal language called Ergo 3 and some high-level language called Ergo script. And the idea is the same. So we have protecting script for a digital coin, right, a digital node. And this script is simply a logic condition, which is combining some statements about secret information and some statements about blockchain context, right? So the very simple example, this condition. So if height is more than 10 and the public key 1 or public key 2. So when spending happens, right? So when we are executing the program, we are using a blockchain context. And then for this example, two possibilities we have, right? So if height is no more than 10, then the script is reduced to just public key 2. So by providing a signature according to public key 2, you may spend a coin. Otherwise, if height is more than 10, then it's about public key 1 or public key 2. And we are using not ECDSA, but some more complicated stuff called generalized Schnorr proofs. So some generalization of Schnorr signature scheme. And these generalized Schnorr proofs do have some interesting properties. In particular, they are preserving zero knowledge, right? So if there is such condition as public key 1 or public key 2, then a signature does not reveal which key was used actually in signing, right? So you can have a ring signature for free, basically. All right, and context we are using in execution is richer than in Bitcoin, but still very lean. So just last few block headers, pre-header of block coming, right? And spending transaction itself. This is very important, by the way. Think that we have spending transaction itself being projected into execution context. And this link context is friendly to stateless and light clients, so they don't have to download much to check any transaction. All right, also we have strict types, and you simply cannot submit wrongly typed expression to the blockchain. We have collections. We have limited set of operations, and because of limited set of operations and some context which is lean, and because we don't allow to create collections on the fly, we can do ahead of time complexity estimation. So even before executing a script, we can say how costly it is to run it. All right. Also, we add additional data registers into a coin. Now we called this box because this is now not just about money, but about some data, and ERG value, monetary value of a coin is just a register, right? There are some registers with predefined semantics. And also we allow to have custom tokens as first-class citizens. Some details follow. All right, so let's start with a dummy example. So counter. So in the real world, this example is very strange, right? So I'm going to set a following contract for this node. So I have a counter in this node. and you cannot spend this node, you can just recreate it with spending transaction with an counter being increased, right? So the condition is simple. For example, if counter is residing in the register R4, then I'm requiring a specific output to have increased value for this counter, and also to preserve a monetary value, right, of a digital node, and also the contract itself. So you cannot freely spend the digital node then, because a spending transaction must recreate the same, right, digital node with the same contract, the same value, but increased counter. Pretty dumb example, but we can do more. So there is a very simple cellular automaton which is called rule 110. This rule is about 8 rules to rewrite 3 bits from upper row to 1 bit of bottom row, right? And what's exciting about this system is that this system is Turing complete. There is proof that you can encode any program to cellular automaton, right? And then we have a proof that Ergo blockchain is indeed Turing complete, because we can implement this rule 110 by having digital nodes carrying bits, right? And modifying, and the spending transaction must modify bits in a proper way, which is pretty useless in practice, but in theory, this means that the Ergo blockchain is Turing complete, and the proof is formal. You know, what's conclusion from that is that Turing completeness is nothing but marketing buzz, right? So users don't need for Turing completeness. They need for some concrete applications to be built on top of the blockchain, right? All right, so what's about practical examples? So first example is about crowdfunding, right? So let's consider the simple Kickstarter-like crowdfunding campaign. Which is about a user is providing funds to a project, right, with known public key, if it's raising no less than some threshold amount of ERGs before a deadline. Otherwise, funds must be returned, right? How that could be? So let's imagine that a single transaction can collect all the needed amounts, right? So no less than the threshold amount. And then this transaction could be huge. So in Bitcoin, it could be up to 22,000 inputs, right? And there is only one output, right? So there are many user boxes, user nodes, right, coming into spending transaction, and only one output if project is successfully collecting money. Otherwise, users are getting money back. And what's in the user box 1, for example, and actually every user box? The contract is pretty much what I said. So after deadline, a node could be claimed by a user, right? And before deadline, it could be claimed by a project if spending transaction is creating output which has value not less than needed, right? And if this output is protected by the project public key, right? And then we have just simple logic OR, right, of two statements. So that's an easy way to do crowdfunding, right? Now we are going to more complicated example. So what also we have in Ergo is a notion of data input. So input could be only read by transaction. So there is a special collection of so-called data inputs which could be only read. So this is an easy way to read arbitrary data from the current UTXO set. Right, so now we can read everything from the current state. And another thing, so you probably know Merkle tree from Bitcoin, right? So Merkle tree is some way to cryptographically authenticate possibly many chunks of data with just one hash, for example, of 32 bytes. So instead of having megabytes or gigabytes on blockchain, you can have just 32 bytes without any chance to modify even a bit, right, in the data set. And we have similar data structure, but more complicated dynamic tree, AVL tree. And we can put root hash and also operation flags in some special data type, AVL tree type. So this type is a tuple which contains root hash and also flags for operations allowed. So there are three types of operations, so insert, update, and remove, right? So instead of storing a big data set, we can store only about 40 bytes, right? And modifications could be checked on chain if needed. And in order to get something from this tree, from the data set authenticated by the tree, lookup proof or modification proof if we modify a tree, so a proof should be provided within a spending transaction. So why is it good? So instead of storing a lot of data in the current state and then have the same problems Ethereum has with its bold state, we can have a very lean state, right? So it is much easier to solve problems with transactions, big transactions, right? Than problems with the big state. Right, and also we have tokens. So tokens are stored simply as a collection in a register R2, and a transaction can issue one token, right? And identifier of this token should be equal to identifier of the first input. So input has some cryptographically strong unique identifier. Then this token is also unique, so you can be sure that previously such token was not created, right? And tokens are stored in R2 register of a box as a map, so there could be many tokens per box, right? And many tokens per transaction. All right. And with these tools, I'm going to explain how to create a local exchange trading system on top of Ergo blockchain. So local exchange trading system is kind of a community currency. So it is kind of local mutual credit system where members are allowed to create debt notes individually, right? And these debt notes are accepted within the community. So, for example, if Alice and Bob are making a deal, so they agree on a price in the first place, and then if the price is 5, for example, then after a deal, Alice's balance is -5, Bob is 5, and now Bob can buy something from Carol with his 5, okay? And such systems are usually small, about 200 members, so usually some village or some local community. Internal tokens of this system usually tied to a national currency. These systems are historically popular when a country is in economic problems or banking crisis, like Argentina 2001 crisis. So during this crisis, there were about 1 million users in Argentina. So they had a lot of local communities and also some exchange networks to exchange tokens within the networks, between the networks, I mean. All right, so usually such system is using a committee of trusted members to add new members and maintain a common ledger. But now we have blockchain, so common ledger is coming for free, right? So we need to have a committee to add new members only. This let's example is about two interacting contracts, actually. So first contract is a management contract to add new members, right? So in order to authenticate this contract, right, a box with this contract, because we don't have long-lived accounts here, we have only one-time coins, one-time boxes. So we need first to issue some management token, right, to designate this contract, and then transaction which is about adding a new member is preserving this management token and also adding a new user token to the tree, right? So this transaction is also issuing new token. It is creating a new user box with this new token and the management token being preserved, etc. Right, so I'm not providing the full script, only a token check and yeah, the transformation part. All right, so now we have new users, right, by running this contract. For example, user Alice and user Bob, right? And now they can do exchange without the committee. In opposite to paper versions of Let's. So now Alice has her box with exchange script, and Bob has his box with the same script, right? And they have the initial balance in the register R4 of 0, right? And then the script is checking that both boxes are recreated with the same exchange script, right, with the same tokens designating users and with proper balance modification. And this transaction is using management box as data input, so it's read-only input, right?
How much more is left? How much more?
3 minutes. All right. So exchange script is checking that all the things are done properly, right? So that's it. And even more, we have already initial coin offering scenario example, which is also about playing with trees and about these 3 stages. So in the first funding stage, users are adding themselves to the tree. So they bring Ergs, right, to project box, and they are adding themselves to a registry of investors, right? And tree is insert only at this stage. Then fixing stage is about a new token to be issued, right, to be spread around investors with amounts equal to amount of Ergs collected. Tree becomes remove only at this stage, and project may withdraw funds from now. And then withdrawal stage is about actual money withdrawals by users. So it's about the same digital note, right? Which is going through 3 stages. So pretty complicated contract, but we have it. Which means that we can do 99% of Ethereum use cases, because 99% of Ethereum use cases are about ICOs and Ponzi schemes, right? Also, we can easily do some things infeasible to do with Ethereum, like ring signatures. So it's very expensive to do ring signatures on top of Ethereum. They are coming almost for free in Ergo. So we don't have bold states, so scalability issues like in Ethereum, right? So we have pretty much the same UTXO set as in Bitcoin, almost the same, but yeah, now we can do the same things as in Ethereum, right? And also we don't have a safety issue because the contract is whether modifying UTXO set as described in the contract, or it is not modifying UTXO set at all, right? So in Ethereum, this is not the case because you can have out of gas exception on the way or some reentrancy or whatever, so you can have broken state, right, somewhere. And we have complexity estimation to be done ahead of time to prevent denial of service attacks, right? Now, some words about Ergo in general. So, Ergo supports partially stateless clients, so you can have a full node without storing UTXO set. If you do not mine, so only miners do need to have UTXO set, and they providing proofs of UTXO set transformations. We have better light client support. We have storage range, so you cannot store forever for free in the Ergo blockchain. We have pull resistant and ASIC resistant, controversial term, proof of work, right? We have parameters change via miners voting. So miners, for example, can vote for changing block size within certain limits. We have new computational model I just described. So it's kind of real Bitcoin 2.0, another controversial term. All right. So testnet is running now. Mainnet launches in coming weeks. We have GPU miner for CUDA, so please play. White paper is coming. We do have a website. What else? There are some links, some tutorials. We have much more examples, so cold wallets, mixing example, and so on and so on. That's it. Questions?
Questions, anyone?
I think you mentioned that a malicious actor can submit a contract to Ethereum, which will take 6 hours to complete, right? Did I understand correctly?
Please repeat the question.
So malicious actor can submit contracts which is taking 6 hours to be validated. It was actually about Bitcoin, not Ethereum. So in Bitcoin, it was found.
So anyway, but you're saying for Ethereum, there's a possibility of denial of service because the contract turns out to be more complex than was.
For Ethereum, possibility of denial of service. So there were many denial of service attacks against Ethereum back in 2016, autumn 2016.
Your script, I think you mentioned also that it is Turing complete or something like that, right?
Theoretically, Turing complete.
Okay, so doesn't that mean that this malicious script can be ported to Ergo script so that
Oh. But wait, it is theoretically Turing complete because we can do this rule 110, right? But in practice, if you are going to do something with rule 110, then you need to have trillions of transactions, right? Modifying your Celer automaton. So.
But does it mean that basically anything can be programmed in your script and therefore also?
Yeah, theoretically, you can do anything can be programmed in Ergo. Theoretically, yes. In practice, there are some limits, definitely. So you cannot do anything, as well as in case of Ethereum. So in Ethereum, right, it's basically the same. So each step, right, has limits of computational complexity expressed via gas, right? So you cannot do within one step of your contract more computations than now it's about 6 million of gas, right? So you can do a contract of 1 million steps, for example. But then you need to wait for thousands of years, right? No, not thousands, but for many years, yeah. In order for your contract to be completed. I mean, even if this contract is taking all the blockchain space, right? Which is not realistic as well. And this is actually is not a theoretical issue. So it was an AmbiSafe case back in 2016. So during denial of service attacks, right? So before attacks, gas limit was about 4 millions per block. And after attacks started, so miners lowered the limit to about 500K, right? And it was some contracts which AmbiSafe company startup deployed to their clients, which was about 2 million of gas for initialization, right? So the company essentially got out of business by miners, right? Just because they lowered this limit. And they did write some open letters to the miners community without any result and so on. So you can read about this story. So sometimes these issues are not theoretical even.
Other questions? So what about what you were saying before about block size?
Block size. So miners,
Unlimited block size.
yeah, miners can change block size. So by default, we have 2 minutes between blocks in Ethereum, and block size limit is about 500 kilobytes, something like that. All right, and if miners are willing to increase block size, a miner can start voting in the first block of a voting epoch. So time is broken into epochs in Ergo. So epoch is being used for difficulty readjustment, like in Bitcoin. But also a miner can propose a voting to be started at the first block of the voting epoch, which is the same as difficulty readjustment epoch. And if 50+% of miners do vote yes during the epoch, then starting from the next epoch, block size being increased by 1%. And in the same way, they can also lower the block size limit. So miners can readjust system parameters in Ergo. And for stuff like block size, it is about 50%. Of miners also can vote for soft forks. This is about longer voting then, definitely. And this is about 90+% miners to vote yes. That's it.
Thanks. Any other questions? All right, we're going to take another break. So the bar is
Thank you very much.
open. Thanks very much.